last class we talked about the how do we quantify this polarization of the light using Stokes vector. In today's class we will talk about how do we quantify the polarization using the Jones vector. So Jones vector, again, it's a kind of another approach to take on the polarization. Jones vector is a matrix again of 2 by 1. If you remember the Stokes vector, it is a matrix of 4 by 1, and in the case of Jones vector, as you can see, it's a 2 by 1 matrix. You have Ex and Ey component, and it can be either given in this form, that is you take Ex outside and you can take 1 by 1 and Ey by Ex, or in the unit form, that is form which is kind of majorly used in unit length. So you take a normalization, that is just square root of Ex square plus Ey square, and in over here you just write what is the Ex and Ey component over here. So for example, when you have a horizontal polarized light source, like you are moving along this path and your electrical field is polarized in horizontal direction. So electrical field is oscillating like this and moving towards the camera. Okay, so that is horizontal polarization. So in that case, you have the Ex component to be 1, and because there is no oscillation in Y component, that is vertical direction, so Y component would be 0. Okay, so the Jones vector for the horizontal polarization is 1 and 0. Similarly, for vertical polarization, that is your electrical field which is oscillating in vertical direction and you are moving in this direction, that is towards the camera. In that case, it is vertically polarized, that is you have the polarization in 0 and 1. The Ex part is 0 while Ey part is 1. So you can see from here as well, Ex, in this case Ex is 1 in horizontal direction polarization, in this case Ey is 1, that is in vertical direction. Now in the case of 45 degrees of polarization, so example you have this and this, this is Ex, this is Ey, but now your polarization is not along any of these original axis, but it's making a particular angle 45 degrees with the vertical axis, for example, right. So in that case, your Jones vector for that particular polarization changes. So you can write it, your both Ex and Ey component would be 1, and then you have 1 by square root of 2, that is all coming into the picture over here. So it's actually square root of 1 plus 1, which becomes square root of 2. Okay. Now we are now talking about this linear polarized light source, that is horizontal direction, vertical direction in a particular angle. It could be at any particular angle. So you use a cos theta, sin theta to change at the particular angle that we will see in some time. Now you could also want to find what is the Jones vector for a circularly polarized light source. So you see the electrical field is polarized in circular direction and moving towards you. Okay, or it could be in opposite direction, that is left circular polarized and moving towards you. Okay, so it could be both circular or horizontal polarized light source. Now how do we quantify that in form of Jones vector, right? So now the first thing is to know some mathematics, that is how do we differentiate a phase shift of 90 degrees. So if you say in the form of complex terms, 90 degree phase shift is given by exponential of minus pi by 2. Okay, now if you see the Euler's formula, you have exponential I theta equal to cos theta plus I of sin theta, and if you put the value of theta as pi by 2, that's what I was suggesting over here, that either it is a positive phase shift or a negative phase shift, right. In the case of positive phase shift, it's plus I, and in case of negative phase shift of 90 degrees, it's minus of pi by 2. So it's like exponential minus pi by 2. Now if you see that exponential of plus pi by 2 is I, if you calculate it out, and exponential of minus pi by 2 is equal to minus of I. Okay. Now if you see the case of circularly polarized light source, we can actually create a circularly polarized light source, either a right circular polarized light source or left circular polarized light source, by adding two plane waves. Okay. Earlier we talked about horizontal polarized light source, so that is a plane wave polarized in horizontal direction, right. Now if I superimpose my horizontally polarized light source with a vertically polarized light source, but both the plane waves are having a phase shift of 90 degrees. Okay, if I superimpose a horizontally polarized plane wave and a vertically polarized plane wave, and the only thing is that the phase shift between horizontal and vertical polarized light source plane wave is 90 degrees. Okay, so how do I write it in terms of Jones vector? So I am going to superimpose. So I have 1 0 for horizontally polarized light source and 0 1 for vertically polarized light source. But what extra that I want to add is there should be 90 degrees phase shift, right? So that I am going to introduce by 1 and exponentially 1 and exponential minus pi by 2. Okay, so this is how I write it for a right circular polarized light source. Okay, so I can again write this as minus pi. Okay, and so you can understand, right? So you just need to multiply both of them together and just add a phase shift of exponential minus pi by 2, that is nothing but equal to minus pi. That's what you get for the circular polarized light source. Now you can have both the direction. It could be phase shifted by 90 degrees, positive 90 degrees, or phase shifted by minus 90 degrees. So you can have either of both the cases. So this comes 1 by square root 2. 1 by square root of 2 comes from the normalization factor. So I want to make it a unit length, so that's what it's coming up. But actually it's around 1 and minus I is for right circular polarized light source, and 1 and I is for left circular polarized light source. Okay, that's how you actually quantify the right circular polarized light source or left circularly polarized light source using the Jones vector. Okay. So this is how you differentiate between Stokes vector and Jones vector. So if you see the horizontal polarized state for Stokes vector is 1 1 0 1, if you remember it, but in the case of Jones vector is 1 and 0. Okay, it's kind of more simplified version. Vertical polarization state is 1 minus 1 0 0. In the case of Jones vector is 0 1. A plane wave polarized in a particular angle, for example 45 degrees, is 1 0 1 1 0, but in the case of Jones vector is 1 1, and you have a normalization of 1 by square root of 2. And similarly it goes for minus 45 degrees. Then you have circularly polarized light source in right circular polarized light source, and then you have left circularly polarized light source. So all of them can be quantified in terms of Stokes vector and Jones vector. However, Jones vector also has a kind of limitation, that is with Jones vector you cannot define something which is unpolarized. Okay, so in the case of Stokes vector you can still define something which is kind of unpolarized light source, but in Jones vector we have to assume a particular direction of polarization. So that is a limitation of the Jones vector that you observe while you actually work with the actual optical systems. Okay, so now let us talk about effect on polarization. Now I want to find the so what is happening over here? I have an input polarization and I am converting an input polarization into something which is output polarization. Okay, so I have input and output. Now if my input is a matrix of 2 by 1 and my output polarization is of matrix 2 by 1, now I need to convert a matrix of 2 by 1 to another 2 by 1 matrix. So how do I convert it? I convert it using a matrix, a 2 by 2 matrix. Okay, so I need to transform my initial matrix of 2 by 1 with a matrix of 2 by 2, and what I get eventually is actually 2 by 1. Okay, for example, now let us see, for example, my input polarization over here is given by Jones vector, that is Ex and Ey. Okay, that is my input polarization. Okay, now I want to convert it into something like Ex and 0, that is a horizontally polarized light source, right? So I want to convert Ex and Ey component of a matrix into a horizontally polarized light source. Okay, this is also a kind of a light source which has both the components, Ex and Ey component, and I'm giving over here this as Ex and 0, that is completely horizontally polarized light source. Now when will that happen? That will only happen when this lens over here is a horizontal polarizer. Okay, so this not a lens, this this optical element has to be an horizontal polarizer. Okay, only then you will have something like Ex and 0, that is only the X component of your electrical field is going to propagate out. Okay, so now if you want to if you want to see how is the mathematics, so if you define the output polarization state as E1 and input polarization state as E0, you can write is E1 is equal to Ax, that is the matrix of the element, optical element, and multiplied by E0. That is for a single element. We will see after some time how we have multiple elements, what does this transformation looks like. So E naught is nothing but Ex and Ey, and I multiply with a matrix that is 1 0 0 0, and I get something known as Ex and 0. Okay, so this is my output, this is my input, and this is my transformation matrix, which is also known as a Jones matrix, because I'm converting a Jones vector into another Jones vector. So this is kind of known as Jones matrix. Similar to this, we are also going to work with Stokes vector. Okay, we're going to see that one Stokes vector is going to convert it into another Stokes vector, and then we'll see that the matrix is not known as a Stokes matrix, but it's known as Mueller matrix. After some time, that you will see that. Okay, now similar to this, now I'm converting a initial polarization state of Ex, Ey to Ex and 0. I get a Jones matrix of 1 0 0 0. Okay. But if I so this is a horizontal polarized light source. Right now, instead of this, I am going to make it a vertically polarized light source. Right. So I have an input of Ex and Ey, and in my output it is a vertically polarized light source. Now, if it is a vertically polarized light source, that means it is Jones vector of 0 and Ey. Now, can you think about it? You can just pause this video and think about how has to be the matrix. Okay, can you do a reverse kind of a thought process, and what has to be the matrix over here, so that you will get something known as 0 and Ey. Okay, so it has to be 0 0 0 1. Okay, so a horizontal polarizer, or also known as X polarizer, is given by a Jones matrix of 0 0 1 0 0 0. But a vertically polarizer, or a Y polarizer, is given by a Jones matrix of 0 0 0 1. Okay, so that's how you define the Jones matrix for each of the optical element. Okay, the state of polarization is given by Jones vector, and each optical element is given by Jones matrix. Okay, cool. So now let us go for another example. Now we have a instead of a horizontal polarizer or a vertical polarizer, we have something known as half plate. Okay. Now half plate is also known as half wave retarder. Now what is the what does it do? So it actually converts an electrical field, or you can see a polarized light source which is around 45 degrees or any particular theta degrees, and it just shifts it to 90 degrees. It just shifts the polarization from for example vertical to horizontal, or it has theta, then it just shifts to 90 plus theta. Okay, just a shift 90 degree in this case is clockwise direction. Okay, so now if you see the Jones vector of the input, that is the input polarization state, it's around 1 1. Okay, if you see the output polarization state, it is 1 minus 1, because it's shifted over this side over here, this quadrant over here. Okay, so what has to be the matrix which converts 1 1 to 1 minus 1? Okay, so if you see, this is the matrix. So my input is 1 1, and I apply it with a matrix of 1 0 0 minus 1, then I get something known as 1 minus 1. Okay, so this is the half plate with which we can convert polarizer with a light polarizer in positive 45 degrees and convert it into a state of polarization again at minus 45 degrees. Okay, plus 45 degrees to minus 45 degrees polarization state. Okay, so similarly, if I convert from 45 to minus 45, okay, or I convert from minus 45 to 45, okay, both the ways you can see I convert 1 1 to 1 minus 1, or I convert 1 minus 1 to 1 1. Okay, so I can use the same Jones matrix. Okay, so I need to use the same 1 0 0 minus 1. So I need to apply the same matrix by converting from 45 degrees to minus 45 and the minus 45 to 45 degrees polarization. Okay, so that is the Jones vector of a half wave retarder or a half plate. Now is one more optical element known as quarter wave plate. Okay, a quarter wave plate, what does it do is that if you shine a plane wave which is polarized in 45 degrees to the fast axis, okay, is the fast axis. This was same thing was there in the earlier case as well, I forgot to mention it. So this 45, this theta is with respect to the fast axis of the half plate. Okay. So in this case also we have a fast axis or the transmission axis is called for the quarter wave retarder. So it's actually mentioned on that particular crystal. Now what I am shining is a plane wave polarized in 45 degrees, and I am shining 45 degrees to the fast axis of my quarter wave plate. Now what does it do is that it converts it into a right circular polarized light source. Okay. So I convert from 45 degrees, I give it to a quarter wave plate, and I get it right circular polarized light source. Can you think about if I want to get a left circular polarized light source, what has to be the polarization? Any guess? Just think about it. We will come to that in some time. So now, light polarized in 45 degrees is 1 1. Right circular polarized light source is 1 and j. Okay. So what has to be the matrix, Jones matrix for the quarter wave plate? You can just see directly. You can write 1 1 is the input, and I need to multiply it by 1 0 0 j, and I get something known as 1 j. Okay. So this is my output. Okay. This is my input. This is my Jones matrix of my quarter wave retarder. Okay. So similarly, if I convert from 45 degrees to right circular polarized light source, I use the matrix 1 0 0 j. Right. Now similarly, if I have minus 45 degree polarized light source and I convert it into a left circular polarized light source using a quarter wave plate again, I can use the same Jones matrix. Okay. So the same Jones matrix of that quarter wave plate that I can use to convert from a positive 45 degrees to right circular polarized light source, or minus 45 degrees to left circular polarized light source. So it's actually it's a quarter wave plate has a constant Jones matrix. Half plate also have a constant Jones matrix. So every one of them has their own matrix, Jones matrix, and based upon what you excite to them, you can get what is the output, whether you want a circular polarized light source or a right circular polarized light source. Okay, now till now we were talking about only a single optical element. Let it be a polarizer, X polarizer, Y polarizer, or it's a half plate or a quarter wave plate. But what if we want a series of optical elements? Okay, for example, I want to have a polarizer. After that, I want to have a quarter wave plate, or I want to have a half plate. So what happens to these mathematics of multiple optical elements or devices? Okay. So here you can see in the input I have E0, that is my vector of 2 by 1. Output is again a vector of 2 by 1, yeah, 2 by 1. And then they have, for each optical devices we have a Jones matrix. Okay, Jones matrix of the first element, Jones matrix of the second element, and Jones matrix of the third element. Now I need to write how E1 is a function of E0. Now the way to write it is a multiplication of the matrices. So if you see, there was only one in our earlier cases. We wrote only A1 into A1 into E0 in our earlier cases, but now we have 3 of them. Now if there are multiples, we have to move from right to left. Okay, in this case I have to write A3, A2, A1 into E0. So have to move from right to left. Now this order is kind of counterintuitive, but it is what is it is required. This order is kind of very much required to get the correct output. Okay, if you don't follow this order, then you might get something which is not kind of correct. Okay, so let us see an example. So here I have E0 and I have E1, which is output, E0 is input. I have X polarizer, that is horizontal polarizer, Y polarizer, LP means linear polarizer. Okay, so this is horizontal polarizer, vertical polarizer. So so if you see, I just do the matrix multiplication. So AY is given by 1 0 0 0, that is vertical polarizer, Ax is given by horizontal polarizer. So you know the matrix, Jones matrix, that is 0, 0, 0, 1, we just discussed some time back, and you just multiply it out and you get it something like 0, 0, 0, 0, 0. So if you intuitively also think, what you think is that you have a horizontal polarizer and then you have vertical polarizer, and you shine any kind of a light source, even if it is unpolarized light source, but nothing will always come out. Because intuitively also, if you think you have horizontal polarizer, which will give you horizontally polarized light source. Now if you have a horizontal polarized light source, if you give it to a vertical polarizer, of course nothing will actually come out. But if you want to put it in terms of mathematics, this is how you can put it. Okay, the matrix has kind of 0, 0, 0, 0. So whatever is the input, your output will always be 0. Okay. So now one more example where you shine a light E0 and you get an output of E1. Both of them are Jones vector, and we have three optical elements now. The first one is horizontal polarizer, second one is 45-degree polarizer, and then you have vertical polarizer. So let us see what happens to that case. So you just need to multiply all three matrices. So AY is given by 0, 0, 0, 1. LP of 45 is given by either you can take half outside and then just write 1, 1, 1, 1, or you can put one half, 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 and then you have the horizontal polarizer, that is you have 1, 0, 0, 0. Okay. So you can see if you multiply all the three together, you get something known as 0, 0, half, and 0. Okay. So this is the transfer function that I am trying to get. So so this transfer function is kind of a very known term in terms of control systems, but it's used also in the terms of optics over here. Right. So your transfer function actually becomes 0, 0, half, and 0. So transfer function, how do you define it? Is nothing but output by input. So your output is nothing but E1, input is E0. So your E1 by E0 is equal to 0, 0, half, 0. Or if you see, if you shine a light source, any light source, so I am writing as Ex, Ey, and In is just there for mentioning that it is an input. Okay, this is a E0 actually. So I shine something of this sort, what I get is something like 0, half of Ex. Okay, so whatever component was there for Ex, it just becomes half. All the term in Y actually becomes so this is the Y component becomes a part of the half of the X component. Okay, the X component becomes almost 0 in this case. So this is the response of this particular optical system of three elements. Okay, so if you want to learn more about it, I will recommend you go to this video. It has a very nice way to quantify the light source for different polarization states as well. Okay, so these are a few of the applications of polarization. One of the application is to quantify so this is a histological, so what do you do is that you, if you have first they actually, so for example, if a patient is going for a diagnosis of a particular cancer, for example oral cancer, now the doctor actually first sees visually inside the oral cavity. Now if they find something suspicious, what they do is that they take a biopsy. A biopsy is a small chunk of tissue from the region which they find to be suspicious. Now what they do is that they take that tissue, they freeze it at a very low temperature, and then they slice that tissue into hundreds of micrometers. Those slices of tissue, they then stain it and then put it under the microscope, under a bright field microscope, and you see something like this. Okay, so this is the same biopsy, small thin slice of tissue under the bright field microscope. Now you shine the light source and you try to understand various optical properties of those thin tissues. Okay, for example, what we are doing is that we are shining a laser of 914, that is an infrared light source. We first give it to a linear polarizer, then we give it to a quarter wave plate. So what we get is a what do we get? We get a circular polarized light source. Okay, I shine a circular polarized light source on this tissue and I try to trace it along the whole of the slide. Okay, so whole of this slice of the tissue. Okay, and then I have a lens and then I have a polarimeter. So it's the same thing that we discussed earlier. Just rotate the polarizer and you try to see for all the different angles. Okay, and what you get out of it is something known as degree of polarization. So if you work with linear polarization, then you get degree of linear polarization. If you work with circular polarization, like what you are doing over here, you get a degree of circular polarization, right? So you try to see for each instance at the tissue, how much is the tissue is losing its polarization. Okay, from there you get to know whether it is cancer or normal, or if there is kind of inflammation or different kind types of stages of cancer. So all those things you can actually try to estimate from this how much is the loss of polarization once the light interacts with those tissue. So this is, I think, it's work of Nishizawa, and another work is for Doronin. And again, what he is doing is you're shining a laser on a mirror, and then you have a quarter wave plate, and then you have a lens to focus at a particular area, and then the light actually diffuses through this tissue, and then it gets gathered through a lens, through a diaphragm to a polarimeter again. Okay, and then you quantify something known as degree of polarization to know how much is the loss of polarization, and can we actually differentiate from normal to cancer between it. Okay, so that's the summary of the Jones matrix. So first we talk about Stokes vector to define any state of polarization. Then we went to Jones vector to again an alternative approach for the state of polarization. Now we talk about the elements. So elements like X polarizer, Y polarizer, half plate, quarter wave plate. So each of them have a particular Jones matrix. Okay, so for example, you have for horizontal linear polarizer is 1 0 0 0, vertical polarizer is 0 0 0 1, and then for a linear polarizer at 45 degrees is 1 1 1 1 with half which is taken outside, and then for quarter wave plate both vertical as well as horizontal fast axis. This is what it looks like. Okay, so that's all for today's session. In the next session, we'll now move from Jones vector to Stokes vector. Now we'll try to see is there something similar to the Jones vector when we talk about Stokes vector. Okay, and we try to get those matrices for different optical elements. Okay, thank you. See you next time.